The discovery of the cosmic microwave background, CMB, is one of the most significant achievements in modern cosmology. It provided strong evidence for the Big Bang theory and revolutionized our understanding of the early universe. The video of this discovery is a fascinating journey that spans from theoretical predictions to accidental experimental confirmation, leading to a deeper comprehension of the cosmos. The foundation for the CMB's discovery was laid long before its actual detection. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman were exploring the implications of the Big Bang theory, which proposed that the universe began as an extremely hot and dense state. As it expanded, it cooled, and at a certain point, the radiation from the early universe should have become free to travel through space. This radiation, predicted to exist as a remnant of the Big Bang, would have cooled down over billions of years and should now be observable as microwave radiation. Despite these predictions, for many years, little attention was paid to the idea of a detectable cosmic background radiation. Other competing cosmological models, such as the steady-state theory proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi, did not predict such a relic radiation and dominated cosmological discussions at the time. While Gamow, Alpher, and Herman had estimated the temperature of this cosmic radiation to be around 5 Kelvin, their work did not gain widespread recognition. Other theoretical works in the 1950s also suggested the existence of such a background radiation, but due to a lack of observational evidence and limited sensitivity of instruments at the time, the idea remained largely speculative. In the early 1960s, physicists Robert Dicke and Jim Peebles at Princeton University revisited the concept of primordial radiation. They realized that if the universe had indeed begun with a Big Bang, then the residual heat from that event should still be detectable. Dicke and his team set out to develop an experiment to detect this radiation, unaware that another group of scientists would soon stumble upon it by accident. In 1964, Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey, were conducting experiments with a large horn antenna designed for satellite communications. They were not looking for the CMB, but instead were trying to eliminate sources of noise in their radio signals. To their surprise, they found an inexplicable background noise that persisted no matter where they pointed the antenna. The noise was uniform, coming from all directions, and did not correspond to any known sources such as the Milky Way or extragalactic radio emissions. They initially suspected various potential causes, including equipment malfunction, pigeon droppings inside the antenna, and atmospheric interference, but none of these explanations accounted for the persistent signal. Unbeknownst to them, Dicke and Peebles at Princeton had been preparing an experiment to detect precisely such a signal. When Penzias and Wilson consulted with the Princeton group, they quickly realized that they had inadvertently discovered the long-sought-after relic radiation from the Big Bang. The two teams published their findings simultaneously in 1965, with Penzias and Wilson's observational results appearing alongside the Princeton group's theoretical interpretation. The discovery of the CMB provided decisive evidence in favor of the Big Bang theory over the steady-state model, which could not account for such a pervasive background radiation. The CMB was essentially a snapshot of the universe when it was approximately 380,000 years old, at the moment when the primordial plasma cooled enough for atoms to form and radiation to decouple from matter, a process known as recombination. This radiation, which had originally been in the visible and infrared wavelengths, had been stretched due to the expansion of the universe, shifting it into the microwave range. The detection of this relic radiation confirmed the predictions of the Big Bang model and cemented it as the dominant cosmological paradigm. Following the discovery, numerous experiments were conducted to study the CMB in greater detail. In 1990, NASA's Cosmic Background Explorer CMB satellite provided the first detailed measurements of the CMB's temperature fluctuations. The data confirmed that the CMB had a near-perfect blackbody spectrum with a temperature of approximately 2.725 Kelvin, consistent with theoretical expectations. CMB also detected slight anisotropies, or tiny variations in temperature, which were the seeds of the large-scale structure of the universe, galaxies and galaxy clusters. Subsequent missions, such as the Wilkinson Microwave Anisotropy Probe, WMAP, in the 2000s and the Planck satellite in the 2010s, further refined our understanding of these fluctuations, allowing cosmologists to determine key parameters of the universe with unprecedented precision. The discovery of the CMB remains one of the most significant milestones in astrophysics. It not only validated the Big Bang theory, but also opened up new avenues for understanding the universe's composition, age, and evolution. The CMB acts as a cosmic blueprint, providing insights into dark matter, dark energy, and the inflationary epoch that occurred fractions of a second after the Big Bang. Today, the study of the CMB continues to be a major focus in cosmology, with ongoing efforts to analyze its polarization patterns and detect signatures of primordial gravitational waves. Future missions and experiments aim to uncover even more details about the universe's earliest moments, pushing the boundaries of our knowledge ever further. The discovery of the cosmic microwave background is a testament to the power of both theoretical predictions and experimental serendipity. It transformed cosmology from a largely speculative field into a precise science, shaping our understanding of the universe's origins and its fundamental properties. As new technologies and observational techniques emerge, the CMB will continue to serve as a crucial tool for unraveling the deepest mysteries of the cosmos.